রিঅ্যাক্টরে ওই পণ্যগুলো পাঠালে তো আমাদের সব করতে পারে আমরা করে তোমরা ডিস্ট্রিক্টে বানানো যে রাজি হোক আমরা জানিয়েছি তো সব let us start. Okay, so we are very pleased to have with us Dr. Chandan Datta today. And Chandan did his PhD with Professor Pankaj Agarwal at Institute of Physics 2018. And since then he has been in Poland with groups led by two very prominent people. First of all, Konrad Danazek, and then now with Alexander Streltsov. And he's moving to Düsseldorf to work with Professor Dagmar Vaz. And Chandan has already, in the short span of his career, worked on many different topics of quantum information, also quantum sensing. And today he will be speaking on entanglement catalysis for quantum states and noise. You have about 45 minutes for your talk, last 5 or 10 minutes.
Thanks. Thank you for this nice introduction. Thank you, sir, for this nice introduction. And good afternoon to everybody. Today, I'll talk about our recent work on entanglement catalysis for quantum states and noisy channels. Basically, our results on how catalysis enhances bipartite entangled state transformations. So this work has been done recently in collaboration with my colleagues from Warsaw, Varun, Marek, and Alex. So first, I will give a very brief background about exact catalysis in entanglement theory. Then I'll talk about introduce this weakly correlated catalytic LOCC transformation. And then using this, I will show how this bipartite state transformation works here. And then also in this scenario, I will talk about universal catalysis. And also, I will introduce the role of catalysis in asymptotic settings, and then the advantage of catalyst in entanglement distribution and communication via noisy channels. Then finally, I will conclude and say a few considerations. Okay, so quantum resource theories is like a very versatile tool to study various quantum information protocols in information theory. And the framework is so universal that it can be easily adopted to study various resources in quantum information, like starting from quantum entanglement to quantum computing. You can easily adopt this framework and study various resources in quantum information. The basic ingredients behind any resource theory is like you first divide this set of states into two groups, like one consisting of free states and one consisting of resource states. And then you consider the set of allowed operations that keeps these free states invariant, set of free states invariant. So basically these free operations are like a subset of all operations. And then one of the most important questions in resource theory is like state transformation, or more precisely, given a state rho S, what are the states that can be achieved from using under just free operations? What are the state of achievable final states here? Similarly, in resource theory of entanglement also, one of the important questions is what are the entangled state transformations under some free operations? In this theory, these free states are separable states. Just to complete it, bipartite state is called separable if and if only if it can be expressed in this tensor product structure. And in general, in this theory, we consider free operations to be local operations and classical communication. But this operations is practically motivated because the parties are spatially separated, so only local operation is possible. But of course, you can also consider other free operations in this theory, like separable operations, non-entangling operations that preserves this state of separability. And yeah, then one of the important results in this direction was provided by Nielsen. It basically Nielsen measurization completely characterizes bipartite entangled state transformation under LOCC. So basically, psi can be converted into phi via LOCC if and only if these mid coefficients satisfy this following relation for all k, where k from 0 to d minus 1, and d is the local dimension of the universe. Now it is not very difficult to construct two states such that they are incomparable, psi and phi, such that psi cannot be converted to phi or phi cannot be converted. Deterministic. Oh, you can consider probabilistic scenario, but I am excluding that scenario. Only deterministic. However, in some cases, this this transformation is still possible using some additional entangled system. And this additional system remains unchanged in the process, and so we call it as acts like a catalyst in this transformation. Basically, you have phi and you attach a tau, another system, and you do a bigger LOCC on both of these two states. And finally, you will have phi, and this tau remains exactly the same. So this kind of example was first introduced in this paper by Jonathan and Glenn. And after this introduction, there has been a lot of work in this exact entanglement pattern. I'm saying exact because there is. Excuse me, go to the previous. Yeah. Next one. Oh, previous one. Yeah. Just shifting on this one. Yeah. So in the last line, phi AB tends to tau AB. So psi AB is a composite set A and B inverse, and you are attaching another system. So it should be some another, right? It should be some another.
Okay, you imagine psi 1v1 A2b.
Yeah, yeah.
That's all.
Oh, okay.
He's trying to say, okay, with Ali.
So this party, half of the party is with Ali, half of the party with. You can label it like A1, A2. It's just relabeling of the indices. Yeah. Is it right? Okay. And the LOCC is only on like Alice is globally globally means Alice is operating on R side with psi and tau. And same for Bob. So after this introduction by Jonathan and Glenn, there has been a lot of work in this direction on exact catalyst. This exact catalyst means that there is no correlation in the final state and catalyst, and also there is no error allowed in the final system. But this kind of transformation is very stringent because there is no error and also there is no correlation in the system catalyst state. But there has been a lot of work in this direction, and I'm not going into the details of all those works, but you can check our recent review article on this. There we have talked about resource catalyst, role of catalyst in various resource theories, including entanglement. Anyway, so yeah, so one of the most important questions given two states phi and phi, if they are incomparable, how do we know that there exists a catalyst such that phi can be converted into phi? And these questions have been answered by independently by Clemens and Turgut, and they showed that you need to satisfy an infinite set of conditions to check whether phi can be converted to phi or vice versa.
Even under catalyst.
Yeah, even this exact catalyst. whether there exists a pure catalyst state which can convert sign.
And in this work, the amount of entanglement from catalysis is not.
Yeah, not
Bounded.
bounded, but
Very
finite. So you need to check basically like infinite state of conditions to just to know whether a catalytic transformation exists or not. And if you allow a small error in the final state, like you are going from psi to phi, if you allow a small error, then recently Brandau et al. Showed in this paper that basically you need to satisfy this monotonicity condition of Raynier. But still you need to check like infinite family of Raynier to know whether there exists a catalytic transformation or not. So despite significant effort, there is no like finite set of monotones which can tell you whether a catalytic transformation is possible or not till date. But significant progress has been made in this direction. Recently, we showed that for weakly correlated catalysis, we can have a finite set of monotones to know whether a catalyst state exists for bipartite pure state transformation or not.
Yes, Chandan, one question is if this functional form is
Yeah, this is
this is the form.
Yeah.
H is the linear.
this is the linear.
F is very peculiar.
Yeah, this is kind of a peculiar. You can see that there is just a greater than, strict greater than, there is no inequality. So this to get this inequality, you need this small error in the final.
All these F are some convex function.
Yeah, this is okay. Yeah. So just yeah.
This S psi, S psi, these are the
Mid-co-
marginal,
just make coefficients of your
marginal states.
yeah, you mean just these are just squares of mid coefficients.
Spectral of the margin.
Spectral of the market. So now I'll introduce this weakly correlated approximate catalysis, where our interest is to go from rho to arbitrarily close to a state sigma. And for there exists, we also introduce a catalyst here and we perform a LOCC operation on that. And final, there will be a small correlation between the system and the catalyst. And you can see if we trace out the system part from this final state and catalyst, you will get back the catalyst exactly.
So then your catalysis is not pure.
Not pure. You will get back the catalyst exactly for every sequence of your LOCC protocol.
And the earlier slide when you were discussing the catalysis, these are only for the pure states.
Only for pure state.
This result is
Yeah.
So you are generalizing scope, more general
More
scope.
So the error then is in what? Error is in the final
Final system state.
final system.
But catalyst would remain same.
So that way, I don't I have some difficulty in understanding that motivation.
Hmm.
One would rather have a situation where the catalysis may undergo a small error, but the final state remains the same.
Yeah, you can consider that, but
That kind of approach
yeah, there is this kind of approach also in the literature, but there is problem is that you are using a bit of resource from your catalyst. That means your resource is decreasing as well.
you use some resource,
Yeah.
that is.
And you can show that not in entanglement theory, but in also other theory, you can show that if you can use a little amount of entanglement from your catalyst state, you can basically do all state transforms.
There is too
So
much
that
power.
way,
Yeah. And this phenomenon is known as embezzling. But in our case, we are considering that we are not using any resource.
Any resource, so catalyst
Remains
remains
intact, so that we can reuse it again and again. And only there is, we are also allowing a weakly correlation between the system and the catalyst, and this correlation vanishes only in the limit. Okay, so this is your final state after this LOCC protocol on system and catalyst. And this is arbitrarily close to this product form of system and catalyst. But the important part is, if you trace out the system part from this state, you will get this. So, in this weakly correlated catalytic scenario, we showed that if rho s can be transformed into sigma s via asymptotic LOCC with unit rate, then there exists a catalytic LOCC protocol transforming a single copy of rho into a single copy of sigma.
What is asymptotic velocity?
Yeah, I'm coming. So by asymptotic, we means that you have like large copies of rho, and you are asking whether the final state is arbitrarily close to the same number of copies of sigma with vanishingly small error. So this is basically this asymptotic transformation, and this error vanishes only in the limit. And we are saying that whenever there exists a such kind of asymptotic transformation, we also have a single copy transformation, transforming rho into sigma using a catalyst.
But you have considered the same number of copies in the rho and sigma. So if you
That's why
change the,
he's saying unit, no?
yeah, that part is okay. But in the asymptotic transformations, you may actually vary the numbers.
Yeah, you can vary the number.
For the
Yeah, this is, I am just taking unit rho, but you can write it for any other rate also.
Rate also you can write.
Okay.
Means if you have rho to sigma asymptotic rate is R,
Then you consider Rn copies here.
then your single shot level rho to sigma with R probability conclusive transformation is possible.
Yeah, but also you can just consider like Rn, you are considering taking Rn copies here because n doesn't matter here. No?
Yes.
So you start with Rn copies and get like the same number of state here. Okay, now just to give you the idea how this catalyst works here and how we use this asymptotic data basically in the catalyst. So this catalyst is like a big mixed state. You have like so this catalyst is like all these labels. Let's consider this K will be like there are n labels, and for first one we have like n minus 1 copies of sigma. In the next one we put one row here and n minus 2 copies of sigma, and so on. And in the last one you will have only row. And the catalyst is like convex mixture of equal convex mixture of all such possibilities. And this state is distributed among all the parts. And this this register is only with Alice. You don't need it with all the parts. Basically, this is just a register to know which outcome appears.
Why all the means there are two parties?
This is true for multi-part scenario also. So I'm just generalizing it to multi-part. So Alice will perform a projective measurement in this basis, and if she gets an outcome n, then all the parties will perform this LOCC protocol, this asymptotic transformation. Whatever lambda we use for the asymptotic transformation will apply here.
So just for clarification, so the row from the second step onwards is the fresh original row.
Yeah.
You are not actually taking the row which has been modified by.
No.
So this is the fresh original row. So many copies here.
Here I'm just for the mixed state. There are many labels. There is just one single row. This is just for representation purpose. I put row on every label, but it's basically row tensor tau. Just one single row.
One single row. So,
but there are different level of this. So just for representation
but
purpose.
then the second step, okay, second step when you are taking inside the catalyst.
Yeah. So this catalyst depends on this initial state and the final state as well. It heavily depends on this state transformation.
Yeah, because inside the catalyst is row tensor k minus 1.
Yeah. We are taking this. Basically, we are taking this asymptotic thing inside this catalyst. So here there was n minus 1 copy, and we add this 1 copy, so it will be like row n copies of rho, and we use the same asymptotic transformation here, which will transform this to sigma n, this result. Now, Alice will apply a swap unitary. Basically, she will relabel her register. So that means n, she is changing n to 1 and I to I plus 1. So if we do that, then this will be with one register, and these other labels will just go down one. Right? This will be with second, and this final one will be with the nth one. The n minus 1 level will be with now n level. Now all the parties will apply a swap unitary. So that means they will just shift their position from n to 1 and I to I plus 1. That means you will get one, you trace out one sigma from here and put here, and subsequently you shift I to I plus 1. Same for this. So here this will come here, and this will go here this way. Now the final state will be like equal mixture of all such possibilities, just to discard any classical information. And the final state, here I just write everything to be sigma, but this will be like arbitrarily close to sigma, and they are not same for each level. They will be like sigma 1, sigma 2, and the final state will be equal mixture of all such states, and it will be arbitrarily close. You have to show that it will be arbitrarily close to your final target. But the interesting part is, if you trace out this thing, you get back the catalyst exactly, which is same. So that means you can again use this catalyst for another transformation from rho to C. So basically we are using this asymptotic result and showing that there also exists a single copy catalytic velocity transformation between rho and C.
So this asymptotic analysis part you just
put in the
catalysis.
But still, you need to show that this will arbitrarily close to final state, and in the limits, the correlation between this system and catalyst matters.
So in this protocol, Alice is performing this measurement, and so that K measurement, right?
Yeah.
Suppose in a single run, it happens that Alice performs a measurement and collapse to 1. Then the actual state is nothing but rho tensor sigma n minus 1 tensor 1.
Yeah, and then they will do nothing. Only if this register clicks, then they will perform the velocity protocol. For other clicks, they will do nothing. But this remains the same. This swap and the relabeling, that remains. So that's why I'm saying you're probably thinking that it is a probabilistic scenario, but it is not probabilistic, because we are taking convex mixture of all these final states, just to discard this classical information. Okay. So using this, we can show that any state transformation, asymptotic state transformation, you can transform it into a single copy catalytic transform. And this is valid for arbitrary multipartite state transformation. Now we use first entanglement to show that it is a monotone under bipartite state transformation. So first entanglement is defined as this infimum over quantum conditional mutual information over all such extension of rho A. And this is monotone under LOCC, and it is superadditive. And using these two properties, you can show that a bipartite state rho AB can be transformed into another bipartite state via catalytic LOCC if and only if this first entanglement satisfies monotonicity. So first entanglement is monotone under catalytic velocity. Interesting point is this first entanglement is equal to the entanglement entropy for bipartite pure state. This is the Monomer entropy of the reduced density matrix of AHEP. So basically, using these two theorems, theorem 1 and 2, you can say that a pure state IAB can be transformed into another pure state IAB via catalytic velocity if and only if this entanglement entropy of psi is more than or equals to entanglement entropy of psi.
Yeah, but that is expected because you are not using any resource for this conversion.
Yeah, that's true. But the interesting point is that entanglement entropy has no meaning in the single copy scenario. It has only meaning in the asymptotic cases because it defines the rate of asymptotic transformation. But here, using this catalytic LOCC protocol, you are saying that entanglement entropy has a meaning in the single copy level. And it is the amount of entanglement you can use in a single instance of an information theoretic protocol. The maximum amount of entanglement you can use.
This inequality. So you have taken this infimum over all rho AB.
Yeah,
Right?
extension of rho AB.
And is this E is related with what the measurement in distance was there? Is
No,
that-
it doesn't matter. It's just an environment. You are attaching this environment with rho AB. But if you trace out this part, you will get this system rho AB exact. That's all. You have to consider all such infimum. So interesting part is that for single copy catalytic LOCC, this is only one monotone. And if it is satisfied, you know there exists a catalyst. So instead of checking all such like infinite family of inequalities, now you have just a single inequality to check. Okay, so now the point is here, this catalyst heavily relies on this initial state and the initial state and the final state. So this catalyst is valid only for this specific transformation from rho to sigma, and it cannot be used for other transformations. So it is natural to wonder whether there exists a universal catalyst which can catalyze all possible bipartite state transformations. And we answered this question positively in this paper. Basically, it shows that consider a bipartite Hilbert space of arbitrary but finite dimension. And for every non-zero epsilon, there exists a universal catalyst state tau, such that for every pair of pure states which satisfy this monotonicity, there is an LOCC protocol lambda such that you can transform phi to phi with arbitrary accuracy. And at the same time, if you trace out the system part, you get back the catalyst exactly. Just to give you the idea how the proof works. So basically, as this finite dimension, so it is we can discretize the Hilbert space. And this F represents the finite set of pairs of indices such that for every pair this satisfies. And the catalyst will be like collection of all such points. I mean, you discretize these points. So from here to here or here, if it satisfies this inequality, you know what is the catalyst. Or
What is meant by the RS?
RS is these grid points. So for let's say this is R, and for every S which satisfies this inequality, you know what are the catalysts for that transformation. So from you say there is a state here, and you know what are the other states you can achieve using the catalyst. So for one R, those are all A's, collection of A's.
For a given state, how this R is determined?
So you know this Hilbert space. So you just basically discretize this point. Every Hilbert space with a error epsilon. So this is this with
Saying we are given two states, psi and phi. Now, how to determine the value of RN?
we are not like determining this R and A. We are saying that Just basically we discretize the whole space. Now you consider each point in this point.
Means, are you trying to say that at least for some pair of psi phi, there exists a universal catalysis? We are that group we are taking.
No. For every psi and phi in this.
No, this one.
This one for just you consider like one R here. You know what is the state here. You basically discretize these points, no? So you know, and this discretize depends on this epsilon error. So you know the other grid point on this Hilbert scale, and from there you can check this monotonicity condition. If this monotonicity condition is satisfied, then you know what is the catalyst, and those catalyst is basically tau I. So from here to here, let's say it is satisfied, you know what is tau I. From here to here, it is satisfied, you know what is that tau I. And you take collection of all such catalysts, tensor product of all such catalysts, and that will be your big universal catalyst. Now, if your initial and final point are on the grid, then it is easy to see that you can easily transform this to this. But the difficult part is when this is not on the grid. It is somewhere in the middle and you want to transform it from here to here. Then first you have to show that you can go to a nearest grid point deterministically using LOCC. And from there you have to go to using this catalyst state, you have to go to arbitrary close to that. So this was the idea to. And we thought that yeah, this is possible for bipartite pure state. In this Hilbert space structure, you can have universal catalyst.
Now you are come to bipartite. The earlier results was for
This theorem 1 is true for any multipartite
in pure state.
pure or mixed, doesn't matter, multipartite. But this second theorem is only for bipartite state. If we know what is the, for multipartite, if we can say something like this monotonicity condition, then it would be good, but it is difficult for multipartite scenario. Because there are many different classes of entanglement and we don't have a good measure of entanglement here.
If it works, it will work for either the genuine entanglement or
yeah, this will be like a stochastic LOCC classes. You are going to a particular class, either JJ or W. Yeah, if you are talking about in a particular class, then maybe it is possible to define a monotonicity. Okay, now I will introduce this, what is the catalysis thing in asymptotic settings. So basically, a state rho can be converted into another state sigma via asymptotic catalysis with unit rate if there exists a sequence of catalyst states and a sequence of LOCC protocol such that you can transform these n copies of rho into arbitrarily close to sigma n copies of sigma via catalysis. So initially in this theorem, there are only single copy of rho, but here we are using also this introducing the asymptotic thing in the catalysis. And if you trace out this system part, then you get back the catalyst data. And in this scenario, we are saying that a state can be transformed into sigma via asymptotic catalysis with unit rate if and only if there exists a catalytic LOCC transformation converting one copy of rho into one copy of sigma. So basically, asymptotic catalysis is equivalent to single copy catalysis. This direction is very easy to see that if we have a catalytic transformation from rho to sigma, then asymptotic catalysis exists. It's very trivial, but the other way is a bit tricky to solve. So, but here we thought that yeah, this asymptotic transformation is just equivalent to single copy. So you don't need to consider asymptotic scenario in catalytic transformation. You can just consider single copy catalytic transformation, and that would be enough. And this result, I would say, not very new. It was this kind of transformation has been studied before for pure bipartite states. And it has been shown that multiple copy exact catalytic transformation is equivalent to single copy exact catalytic transformation. And this has been done in 2005 by Duan. And our result is more general in the sense that this is true for arbitrary mixed state, arbitrary number of parties, and also we allowed a small error in the final. Okay, so this in this IID scenario, we showed that this is equivalent to single copy catalytic transform. Now I will show that one.
Just put the previous. So here actually, when you are saying single copy things, you are allowing little bit correlations between your catalysis and
Yeah, and this correlation vanishes only in the link.
only in the link. And I think those results are
These are exact.
exact. No?
For the exact. Right now.
That's why it is happening.
Yeah.
You have to allow.
You are getting more power.
Yeah. Okay. Now, one interesting scenario in beyond IID scenario. So here we are considering that Alice and Bob have access to like these pure states, which is like a sequence of pure states. These are not necessarily identical. So we are going beyond IID scenario.
What is IID?
IID means these are like exactly equal in you have like exactly same, and each time you are having like same row, it is not changed.
All are identical.
All are identical.
But in real life,
Like some the errors can be there.
But here in experimentally it is relevant because you always don't have the same like same
error is
row.
not identical.
Yeah. So you can have like a sequence of, or you can say that you want to produce a psi and you are getting all states which is like a ball around epsilon ball around that psi, something like that. So you have like a sequence of pure states here, which are not necessarily identical. And we say that this sequence allows to extract a singlet with fidelity A and a probability P if there exists an integer n and a probabilistic LOCC protocol lambda, such that if you implement this lambda on this sequence of state, you will have P probability that this fidelity between this singlet and this final state is arbitrarily close to 1. So, but in this protocol, I am not saying any catalyst protocol. I am not allowing any catalyst. It's just you have in like sequence of states, and I am also allowing probabilistic scenario here and also approximate scenario here. In the next one, we are saying that we have the same sequence with some.
You are also not getting the singlet exact with
Yeah.
fidelity F you are.
Yeah.
And
Also probability. So without catalyst, I am also allowing probability. You can give me a singlet with this much probability.
But we have to ensure, okay, in this run I have singlet.
Singlet.
It's conclusive. It should be conclusive.
But for the catalyst, we are saying that we can extract n singlets with catalysis for any arbitrary epsilon. There exists an integer n, a catalyst state tau, and an LOCC protocol, such that we can convert this sequence to n singlets, arbitrarily close to m singlets, and if we trace out this system part, we get back the catalyst exactly. So there is just see these two pictures. So here I am allowing probabilistic scenario without catalyst, and here it is deterministic, but with catalyst. And we are saying that given a fidelity which is more than half, and for all epsilon, non-zero epsilon, we can construct a sequence of 2 qubit states such that for any n greater than equals to 1, the probability of converting the state into a singlet via LOCC with fidelity A in this picture is smaller than epsilon. But at the same time, you can have an unbounded number of singlets with certainty from this sequence with the help of catalyst. So there you can see there is a huge advantage. So basically, in this scenario, you will get a singlet with probability which is smaller than epsilon, and epsilon could be arbitrarily small. So basically, you are not getting a singlet in this scenario. But at the same time, if we allow this catalysis, we can have like unbounded amount of things. So basically, the idea is to construct a sequence such that the total entanglement entropy is diverging. But you know that for the probabilistic conversion, the main ingredient is the maximum, the largest Smith coefficient determining this probabilistic conversion. This Vidal result which says that it depends only on this largest Smith coefficient of your state. So you have to construct a sequence such that the total entanglement entropy is diverging, but at the same time, the largest Smith coefficient is arbitrarily close to 1. And we showed that, yeah, we can construct such a sequence. And so in this, like beyond IID scenario, we have a huge advantage of catalysis.
But all Shai are pure, no?
Yes, all five are pure.
But if you so the first Shai one that I don't know actually, it is inside the form. So I can think that this actual state is nothing but some weak state.
No, that is not considered.
No, I am not considering. I'm just giving an example. You can also consider mixed state also. If you can show some advantage, that would be interesting. But that would be very tricky to.
His result is Shai 1, but around this Shai 1, okay, whatever the pure state it can have, it is not identical. That is.
I'm just trying to show an advantage, huge advantage of catalysis. So I just construct a 2-qubit sequence of states such that you cannot get singlet even probabilistically. But at the same time, you can have like unbounded amount of things. And the idea is just to have like diverging amount of you just take a sequence where total entanglement entropy is diverging. But at the same time, the maximum or the largest mid coefficient is arbitrarily close to 1. If it is arbitrarily close to 1, the maximum probability is, I think, 1 minus lambda, something like that. And if it is arbitrarily close to 1, then the probability is just like very close to 0. So there is a huge advantage in this scenario. Okay, now I'll come to this entanglement catalysis for quantum channels for communication and also for entanglement distribution via noisy channels. Just to introduce the picture, we have let's say we have a 2-qubit pure state which is created by Alice locally and then distributed half of it via a noisy quantum channel. And after this, the state will be mixed. And if the distillable entanglement of this state is more than 1, then using our protocol and the catalyst, we can always get a singlet. But in the usual quantum capacity thing, we have like many number of same channels, and we consider whether we can get at what rate we can get a singlet in the final. But in general, if we have just a single copy of channel, it may not be possible to get a singlet every time without a catalyst. But here we are just have a single copy of channel and we are saying that whenever the distillable entanglement is more than 1, we can have a singlet here. But this is not possible if we just have a single instance of a channel and if you don't have catalyst, then it may not be possible to always distill a singlet because you just have one copy of this final. And distillable entanglement, this is defined only in the asymptotic.
The channel has
Just you have one instance of channel. You don't have.
and something, some capacity one from you say what is it, that 1 bit of something?
Yeah, so I'm saying whenever the distillable entanglement of this state is more than 1, you can get a singlet using a catalyst and then
Oh, so I have a tripartite. I prepare a Q-treat system. I send it to the channel, but it becomes a noisy state. But its entanglement is more than 1 at least.
Yeah.
In that case, your result will 1.
Yeah, but I'm saying even if you you have this state, only one copy of this state. In the usual scenario, you cannot distill a sample.
Because it is asymptotic.
Yeah. So in that sense, it is this catalyst is advantageous because you are having just one copy of the channel and you can distill the same there. And we define this capacity thing here, like this maximum number of singlets you can get from this final state. Mu n is just the final state here, system catalyst. And this is arbitrarily close to this catalyst plus this n copies of thing. And the capacity will be this maximum value over all such LOCC protocols and all such catalyst state, and this will be the maximum for such a protocol. And then a channel lambda can transmit m qubits whenever there exists a bipartite state rho such that this distillable entanglement is more than or equal to m. Whenever this distillable entanglement is more than m, you can just basically have like m single. And distillable entanglement is lower bounded by this point, so it is very easy to calculate. And even for like Bell diagonal state or maximally correlated state, I guess this is equal. So this you can easily calculate this thing. And if you calculate this thing for starting from a maximally entangled state, you can send m singlets via a noisy channel if this equation is satisfied. We can also give an upper bound when a channel cannot transmit m qubits. And this is upper bounded by this transmitted entanglement through this channel, which is thus this transmitted sparse entanglement through the channel. So I'm not going into the details of this proof, but the thing is here this capacity, catalytic capacity is very difficult to calculate because there is a lot of optimization and these protocols. But we have basically two bounds. One is this distillable lower bound on distillable entanglement, and we have an upper.
That bound is required because
You know when you can send anything, this lower bound.
exactly because suppose I have a qubit channel and for a single copy of a qubit channel, let's take a qubit channel.
But for qubit channel, I don't think it will not work
It
because
will not work because it would then it would, in the presence of catalytic it would increase the entanglement.
yes,
That's why it is not possible. That's why that demand is necessary that the final state's entanglement should be higher than the 5 plus.
yeah, or equal.
Or
Otherwise, you cannot distill because you can see this is just an integer.
exactly.
Capacity is just an integer. So you can have like 1, 2, 3. So yeah, but this catalytic capacity can exactly be calculated for some channels like Pauli channels. And these Pauli channels, the work of a Pauli channel on a state rho is just this mixture of all these sigma matrices on this state rho. And for any quantum channel, we have this bound on capacity. I just put ceiling because this is an integer. So I just put this ceiling function on. And for this Pauli channel, we know what is this distillable entanglement exactly because these are just Bell diagonal state. And for Bell diagonal state, the distillable entanglement is just this. So let's say we have like 2 instances of this Pauli channel, 2 copies of Pauli channel. For these 2 copies, we can calculate.
No, earlier S minus S.
Yeah. This is just
Hashing protocol.
Yeah, this is just coherent inference. Also, this distillable, lower bound not distillable entanglement.
By 1
Yeah. So you can easily calculate this lower bound. For the upper bound, this first entanglement is non-trivial to calculate because there is all such extension involved.
So for polychannels it is additive, right? The distillation.
Yeah, this will just additive. So yeah, that's why for Pauli channels it is very easy to calculate this capacity thing, even in the normal capacity, right? Usual capacity will be fine. Because then we don't need this like infinite like instances of those channels because it just basically add up. So, but this upper bound is tricky to calculate because there is this optimization involved over all such extension of loyalty. But the interesting point is this first entanglement is additive, and this first entanglement for bipartite scenario is upper bounded by entanglement of formation. And for all, like for bell diagonal state, entanglement of formation is known. So basically, for two instances of Pauli channels, it is upper bounded by this entanglement of formation, and which is this. So basically, this Q lambda for this Pauli channels is bounded by this. And in this range, you can show that it is smaller than 2 and it is greater than 1.
Chandan, I think Pauli channel is not additive. For general Pauli channel.
General Pauli channels.
For arbitrary this PI, this thing is not fluent information is not additive.
This is just entropy, no? These are additive.
No,
So it is
No, I am not talking.
it's rho A minus S, rho A B to not be.
it is not additive.
That is coherent information. It's just distillable entanglement of this. So you can add this. This is just entropy. No? Entropy is additive.
No, this is not the entropy. This is the difference between entropy. So it would actually depend on the because your input states when you are taking two channels, two Pauli channels. So your input space is right now C2 tensor C2. You can use some entanglement here, and you can actually get more than whatever the value you have given, more than 2 of 1 minus HPI.
But I guess if you do this calculation, I guess it will be like 2 times 1 minus HPR. We have checked that, and I think it is additive this thing for Pauli channel. Because I'm saying why? Because this Pauli channel, the optimal way to distribute entanglement is just you create a bell state and you send half of it through this channel. And like here, bell state you can like consider 2 copies of bell state, which is same as like a 4-dimensional maximally entangled state. You can convert a 4-dimensional maximally entangled state into like 2 copies of bell state, right? No.
Anyway, we can discuss it later.
Okay. Okay. So yeah, I was just saying that this is 1 and in this range, and it will be 0 when P max is. So you can exactly calculate this capacity. And just to give you this distribution via this catalysis, we consider this single cubic depolarizing channel, which is entanglement breaking in this range, and it allows entanglement distribution only in this range. Now we are introducing a node in between, and we are saying even if this node is able to assist these 2 parties for entanglement distribution, in the usual scenario, the channel will still be entanglement breaking in this range. But if you use the catalyst, and here, as all 2 cubic mixed states are distillable, then we can distill a pure state here using the catalyst, and then we can send that pure state to the other half of the channel. And you can show in this way that the channel can distribute entanglement in this range, almost like double of whatever you are getting in this thing. So there is a huge advantage in this scenario. And just to conclude, so there is offers a significant enhancement for entangled state transformation, and we also showed that entanglement entropy completely characterizes bipartite state transformation. And also we talk about universal catalysis in this scenario, and there is a huge advantage in non-asymptotic non-IID scenarios, and also there is advantage in communication and also in entanglement distribution. Just to give you some future directions, we can consider a catalysis protocol. Here we said that we have whatever we can do in the asymptotic transformation, we can have a single copy catalytic transformation. But we don't know whether single copy catalytic transformation is more advantageous than asymptotic. If we can show that, that would be great. And for an immediate check, we can consider bound entangled state, or let's consider a state transformation where the rate is strictly smaller than 1. But with a catalyst, you can convert a single copy of rho into a single copy of sigma. And in the case of exact catalysis, we don't know whether a mixed catalyst state could enlarge the set of achievable states for a given initial state. Because in the background, all the state transformation was used in a pure catalyst state. So we don't know whether a mixed catalyst state could be advantageous. And these methods can be easily adapted to other like non-locality stabilizer, quantum computation, and dynamical resource theories also. And thank you.
Okay, good. So questions? You were very hard to answer questions by us. I mean, anyway, you could go ahead and ask more questions.
So by adding a catalyst, uh, can we transform and non-maximally entangled state to a maximally entangled state by LOC?
Do you mean that non-maximally it is pure?
Yeah, let's say it is pure.
So if it is 2 Q3 and its entanglement entropy is more than 1, then you can get a best state. Because this only criteria is this state transformation.
But we know that by LOCC we cannot increase entanglement.
But that is LOCC. I am enlarging the state by introducing a catalyst. This is LOCC plus catalyst, not just LOCC.
Does the catalyst is in possession of both parties?
Yeah, of course. Otherwise, there will be, I mean, both the parties have this possession half of it, and they are performing LOCC protocol on that system and catalyst.
So if a single party has in possession of the catalyst, then it is not possible.
Yeah, no. Because then the bomb doesn't have any information about the catalyst. Then it is just the usual LOCC transformation between them.
It's an Anchila straight line. Catalyst is something more than just.
But can you repeat that with the connections with the negativity?
Negativity. Yeah, I haven't presented here, but I can say you this negativity. So this actually only condition for state transformation of bipartite state is this. If this monotonicity is satisfied, then you know that you have a catalyst which can transform this. But there may exist instances, or you can design states like psi and phi, which satisfies this, but their log negativity is opposite direction. Logarithmic negativity of phi is more than logarithmic negativity of phi. But we are saying this is the only condition for state transformation. So even if logarithmic negativity is so opposite direction, you need a huge catalyst or unbounded amount of catalyst to transform this state from side to side. But for other instances, you can have a finite catalyst and transform.
Okay. And actually, you are getting determination. This LOCC transformation from necessity and sufficient conditions to the marginal entropy.
Yeah.
So when this is because of inexact type of catalytic. Because if you do the exact type of catalytic, then this single conditions should not be sufficient. We need all this that could go.
Yeah.
We need all
Exactly.
those. But it is a huge thing actually. You bring it to one quantity.
Yeah, that's why this result is important in the sense that in the single copy also you have just a single monotone which characterize all by matrix transform. And to show this first entanglement is very important.
So I'm just asking a simple question. What is question finally? So let's say I have some state, and I know that by one copy I cannot distribute.
Mhm.
Asymptotically distributable, but one copy I cannot distribute. Using a finite amount of catalysis, I have some distillation rate. Of course, the distillation rate may not be same as this asymptotic.
Oh.
Would it be interesting showing that? Or
Yeah,
is
I mean, practically it could be
it,
important.
is it following from some of your results? It is not following.
No, it does not follow. For that, you need to consider finite dimensional
Finite
case,
dimensional
and
case.
you have to check whether you can transform it.
Means we have to one has to give the exact protocol.
Yeah.
But there is a hint in your, I mean, can you show in the figure where you do the transformation?
Yes.
So like this one. So yeah.
Because you see, there is one result by Professor Linden,
Mhm.
1945. I think 2 qubit mixed state doesn't allow any one shot. One copy distillation is not possible.
Probably.
Even probabilistically it is not. You see, you see, mixed state always one copy distillation protocol exists. Of course, that rate is not asymptotic, but some rate it exists. But for but mixed state is more natural, practically.
Yeah.
Now somebody says, okay, being the catalysis, at least some non-zero rate I can get, and I can get to some pure state.
Yes.
Is it great result? No?
Yeah,
I can
yeah.
use this recursively and actually get back this.
Get back your step.
Yeah, it can be done.
Yeah, if it can be experimentally implemented, that
So
would
that
be.
is the
Yeah, but even in theory, you have only have to show and then.
because but I am trying to say this catalysis we should use bounded because again catalysis is unbounded, then again
Again
we
the
are in
same problem,
asymptotic.
right?
Same problem practically this
Mhm.
difficulty everywhere.
For bounded, you will have some
Protocol we have to give.
your protocol, and this rate will be different, but you can.
What this study is showing, looking into this kind of problem is actually possible.
Yeah, yeah.
Might be
It
there
is
are
possible.
Because he is already, I mean, there are some.
There are some paper like this quantum teleportation calculation. They showed that for some instances you can have like a finite dimensional catalyst and you can transform. Yeah, also in this review we have talked about this like where there are many papers where they have used finite dimensional.
Yeah. So this review that the other paper that you are showing, that is a different one. Huh? Yeah. No. That was an earlier PRL. The one which
yeah,
has
this,
a lot of results.
yeah, yeah,
Later one.
this one.
Later one.
Yeah.
No.
No, yeah,
This one has a lot of results.
Yeah.
Yeah. Okay, but this is in the archive from February.
Yeah.
So almost 1 year. So what is happening? Some problem referees are doing some
Problem referee, we first send it to PRL, then one referee agreed and one referee said that already there is many results in PRL and we don't think we need any more abstract result in this direction.
Anyway, so that is just.
If somebody some finite limit it can happen, then again
Then
they will
of
agree.
course,
because
yeah.
Still
It is
it's
practically,
asymptotic.
practically.
Asymptotic things they have
Yeah.
shown it.
Yeah.
Catalysis.
Anyway, thank you very much. And we will have some tea and coffee and he's around for some.
Sir, I have a question.
Oh, somebody on the online? He's on
Sir,
a,
I'm sir, I have a question. Can I ask?
yeah, ask it and he will answer.
Yeah.
And we are having tea.
Yeah, it's a comment actually. So thank you, Chandanda, for this nice talk. So actually, I would like to say that for in case of non-locality, I think the catalyst thing does not exist.
That's true. There is one paper recently there where they
Yes.
in,
They have shown that
for contextuality, but
yes.
they only allowed exact catalysis. There is no correlation
Okay.
between the final state and there are also no error in the final state.
Oh,
So
I see.
I
Okay.
am just talking about if you allow weakly correlated and approximate in the final state, then we don't know.
Okay. Thank you very much. Thank you.
No problem.